Same problem. Co0 has artificial sweeteners that mess up your metabolism. Pull your brain into thinking weird stuff. All right, guys. Settle in, ladies and gentlemen. Settle in, boys and girls. It's story time. Today's book will be Quantum Physics for Babies. Are you ready? Okay.
Are you trying to say something?
Yes. Quantum Physics for Babies by Chris Furry.
That's pretty obvious.
This is a ball.
Really?
This ball has energy. This is a ball. This ball has 0 energy. All balls are made of atoms. There are neutrons and protons and electrons. Electrons have energy. This electron has the most energy. This electron has the least energy. Energy is quantized. An electron can be here or here or here, but not here or here. There are no electrons with 0 energy. An electron can take energy to jump up and must give energy to fall down. This amount of energy is a quantum. Now, you are quantum physicists. The end.
How much do I get paid? Low key? Yeah. If got all you need in quantum. You just put this book and now we're getting paid to be quantum. This is but we paid for it.
All right. Hope you enjoyed that story. So the next unit, we're going to be here for, it's actually a really, really fast unit because it's hard to do labs with things like electrons without having really, really expensive equipment, which we don't have. So what we're going to be spending time on is talking about electrons. So our first unit, we talked about what's going on in the nucleus.
Now we're talking about what's going on.
Now we're talking about what's going on around the nucleus. Okay? So we remember that there is a nucleus, and inside the nucleus you got some protons with positive charges, and you got some neutrons with no charge. And then around the nucleus you got electrons. Like, hey, electron! Hey, electron! And we're going to learn about those electrons today. This, guys, are you ready?
Yes.
Third row, fourth row, you ready? Okay, so this big mess of numbers makes a lot of sense to chemists. And you'll notice the letters present, there's only 4 letters present. And they are S, P, D, and F. And those are important. And you might notice that the big number goes from 1 to 7. 1, 2, 3, 4, 5, 6, 7, 7. 7, only 7. And then the numbers on top are very specific. They are either a 2, a 6, a 10, or a 14. This is called an electron configuration. An electron configuration is like an address for an atom. Much like you have an address at your house, so when you order something from Amazon, you say, all right, I'm in the United States. I'm in Nevada. I'm in Boulder City. I'm at this street and this number. So they can hone in on you and know, okay, you're in Nevada, you're in Boulder City, you're on that street at that number. They know exactly where to deliver it. Similarly, an electron configuration will tell you exactly what atom you're talking about based on this address. And you can look at the periodic table and you can say, based on the location on the periodic table, I can write its address based on its location. Electron configuration. Okay. Questions before we get started? Well, questions before we continue. All right. Quantum model. Okay, so there's this guy named Niels Bohr. I'm ignoring a whole bunch of atomic history because 3 years ago, CCSD people said, you don't have to teach atomic history anymore. I'm like, okay. So I'm ignoring a whole bunch of atomic history. Just know that there's this guy named Niels Bohr. And this is around the turn of the 20th century, beginning of the 20th century. Our chemistry knowledge was really coming into its own. And we had this idea about electricity. Electricity happened about 20 years earlier. And Niels Bohr said, electrons. Previously, electrons were all in one big shell. So they were all cruising around on the outside of a shell. Think about putting a BB in a beach ball, and then the beach ball had all these electrons around it. Whole bunch of electrons around this tiny little nucleus. And Niels Bohr said, you know what I've noticed? When I electrify atoms, it gives back energy. And it's always of a very specific amount. So to illustrate this, I need a volunteer. Perfect, come on. Like, oh no, it's Matthew. Need that chair, so come on over. I'm gonna use this table right here. So put the chair right here. Now, right now, just for purposes of illustration, you know what? No, right, you're fine here. Okay, so right now, Matthew is on the floor. We're gonna call the floor level 0. Okay? Now, Matthew's about to step up to the chair. We're gonna call the chair level 1. Go ahead and step up to the chair. Okay. Now, what had to happen for him to get to level 1?
He had to acquire energy.
Exactly. His muscles had to use energy to get him up to level 1. He can't just be like, he can't just will himself up. His muscles had to use energy to level 1. Okay, now go to level 2. What had to happen to get from level 1 to level 2?
More energy.
He had to use more energy, right? So, do you think he could have jumped right from level 0 to level 2?
Yeah. Yes.
I think he could handle it. But what would have to happen for him to do that?
A lot of energy.
He'd have to use more energy. So, if he was an electron, we would say level 0 is at 0 units of energy. Level 1, we're going to say is 4 units of energy. And level 2, we're going to say is 9 units of energy. So we had to use 4 to get to level 1, 5 to get to level 2. Or he could have used 9 and go from level 0 right to level 2. Make sense? Atoms do the same thing. Now, this is what I like to do. I'd like you to attempt to be on level 1.2. So right at, or 1.5, right in between. No, now you're resting on level 1. No, right in the middle. Right, just stand right in the middle between level 1 and level 2. Just right there.
I'm sorry.
Okay, now you're on level 2 again. Okay, this is not a hard set of instructions. Okay, yeah, you can't, exactly. You can't be between levels. Okay, so electrons do the same thing. Electrons cannot exist between levels. They can be at 0, called the ground state. They can be 1 level above, or 2 levels above, or 3 levels above, which are kind of called excited states, but they cannot be anywhere in the middle. Thank you,
Okay.
Does this little model make sense to you?
Yeah.
So, what Bohr did is he said, you know what? This idea that all the electrons are surrounding the nucleus at the same shell is not cool. I'm not cool with that. So what we're going to do is we're going to have multiple shells. And electrons are going to exist in multiple shells. And this idea that electrons can gain energy and jump up to a higher level is called the Bohr model. Electrons exist in very specific levels. Now, not only do electrons exist in very specific levels, those levels have an energy capacity, like the size of, like if we thought about electrons as things, we might think of the levels as buckets. Some buckets are bigger than others. Cannon, is this a problem? Do you need to move?
No, I don't want to keep mine.
You're good?
Yeah, I love it.
All right. Because if there's too much distraction, we can move. We can make a change.
No, that's not that.
All right. So in the Bohr model, electrons exist in shells, and shells closer to the nucleus are smaller. So imagine the track right up there.
Yeah.
Right up there. So imagine the track. The track has lanes, and you're supposed to stay in your lane, right? Well, imagine those lanes got smaller and smaller and smaller and smaller to the very center of the track. It's like you just had lane. There's like 30 lanes to the very center of the track. Now, the person in the middle lane, you're like, okay, do 2 laps. And he's like, done. Okay, that's where we put me. So I don't want to exert a lot of energy. I just be like, 2 laps, all right. Don't have to exert very much energy. So the shells close to the nucleus don't have to exert very much energy. Now, 30 lanes out there, that's where we put Cannon. It's like, take 2 laps. Cannon's like, huffing and puffing. He's like, I can do it. But he has to exert a lot more energy, right? Electrons do the same thing. Electrons that are nearest to the nucleus have very little energy. Electrons that are far away from the nucleus have a lot more energy. So we're going to focus on the simplest atom that exists. We're going to focus on hydrogen. Hydrogen has a single proton chilling out in the nucleus, and it's got 1 electron. Now, if I run energy, if I run electricity through hydrogen, that electron is going to absorb a little bit. But the amount it absorbs is a very specific value. It is a quantum of energy. Quantum science is the idea that electrons can absorb energy of a very specific size. No more, no less. Kind of like you're watching your weight and going to eat 400 calories, no more, no less. Yes?
So a quantum is a small packet of energy just in a very specific amount?
Exactly right. A quantum is a very specific amount of energy, a single packet. A quanta is multiple quantums. By the way, did you know data represents a whole bunch of information, and the singular of data is a datum?
Yeah.
So your age is a datum, your name is a datum, and you, all your entire profile is data. Did you guys know that?
Mm-hmm.
Yeah, the plural of datum is data. The singular of data is datum. So the singular of quantum is quantum. The singular of quantum, or the multiple of quantum, is quanta. All right, so a single small packet. Let's say that we're gonna make this level 0. 0, 1, 2, 3. Let's say level 0. The difference between level 0, let's say it's 4 units, because we talked about 4. If it gets 3 units of energy, guess what happens?
What?
Exactly, nothing. It's not enough. If it gets 4 units of energy, then it will jump up and it will become excited. You give it a little asterisk, excited. Okay. So it was previously in its ground state, now it's excited because it got 4 units of energy. If you give it 5 units of energy, guess what happens?
It goes extra.
It still jumps to level 1. So let's say it's just 4 units of energy from here to here. Let's say from here to here it's 6 units of energy. And let's say from here to here it's 8 units of energy.
Yeah.
If I give that ground state electron 3, nothing happens. 2, nothing happens. 1, nothing happens. 4, it jumps up. 5, it still jumps up into the first shell. Because there is no 5 level here. Does that idea make sense?
Yeah.
If I give it 6, guess where it goes?
Go to level 2.
Still level 1. But if I give it 4 and then 6, then it'll jump up. So if I give it 4, it's going to jump up to level 1. If I give it 6 more, it's going to jump up to level 2. Now here it is. What's the energy value up here at level 2? 10. So now it has options. It doesn't want to spend much time up there. Much like you, teenagers, atoms and teenagers would like to get through life with as little energy as possible. So once it's up at level 10, it wants to come back down. So it's got some options. It can jump all the way back down and give off 10 units of energy, giving off its +4 it gained and +6 it gained, or it can jump in 2 levels. It can jump from level 2 to level 1, and then level 1 to level 0. Make sense? Now, each of these jumps corresponds to a photon of light. Photon. Like photon torpedoes. Fire the photon torpedoes! What's a photon? Yeah, it's a burst of light. It is a packet of light. It is a packet of light, and the photons could be radio waves, they could be light waves, they could be infrared waves, they could be all kinds of waves. A photon is a packet of light. So, which has more energy, 4 or 6? 6. So let's say 6 is a green photon. So jumping from 2 to 1 gives off a green photon. Let's say 4, which is less than 6, is a red photon. Make sense? And jumping from 2 down to 0, 10 units would be an ultraviolet photon, UV, very high energy. Does this make sense?
Yes.
So if you ever heard about Roy G. Biv, red is low in energy. You probably heard in geoscience about the colors of planets, or maybe 8th grade. So blue is higher in energy than green, which is higher energy than red, which is higher than energy than infrared. The highest energy in the visible spectrum is violet. And since we're on the subject of planets, what color, sorry, of stars? For those who are in geoscience, you like learn about stars?
Absolutely not.
You never did?
Nope.
Okay, well,
Absolutely not.
Definitely not.
did anybody learn about colors of stars?
Absolutely yes.
Okay, there's like hot stars and cold stars, and they label them blue and brown and white. What color are all stars?
We didn't take geoscience.
White.
Yellow? Oh.
All stars are white. Your sun, by the way, is white. All stars are white.
Really?
Why does it?
Maybe by distance.
Yeah, white is all colors. Stars, main sequence stars are all white. The reason the sun looks yellow is because there's this layer of life-giving gas over the top of you.
What? And that why the sky's blue?
No, the sky is blue for a different reason, but we can talk about that in physics.
Is that because the light waves?
Okay, you know what? We'll talk about why the sky is blue later, but not today. But yeah, so anyway, getting back to my discussion.
Light rays were never.
Is this sun white? Is this sun white?
The sun is white. The sun is white. If you get in a spaceship, fly out of the atmosphere, look at the sun, it's going to be white. If you look at the pictures from Mars, the shadows are red stone lit up by white light. If you look at the moon landing, white light. Not yellow, not red, not blue, or not orange, white.
When are we supposed to learn about these things? If we didn't take
8th grade or geoscience. 8th grade physical science or geoscience. But now you know. So when you take the ACT, you can be like, I'm ready.
I mean.
Okay, guys, let's get back to our discussion. So, if you like animation, here you go. So electrons are in their ground state. They absorb energy of a very specific amount called a what? A quanta, and then it jumps up. Do electrons like to be in their excited state? No. So very quickly, so they're in their excited state, very quickly they come back down, but what happens to that energy? It gets ejected back as a photon. Now here's the cool thing about the energy coming in and energy coming out. Energy is energy. Okay? It can be electrical energy, it can be heat energy, it can be light energy, it can even be thermal energy. Energy comes in and energy comes out. It might not come in the same way as it comes out. Now a mirror absorbs light energy and gives off light energy. That's why you can see your face in a silver mirror. Light energy comes in, bounces off your face, hits the mirror, and it goes in as light energy, and it comes out as light energy. But that's not always the case. I have some crazy devices here invented in the 60s where light energy comes in, and what kind of energy comes out?
Power source.
Electrical energy, yeah. So an electric field gets created. So light energy comes in, electrical energy comes out.
Wait, I have a question. But does the energy create power? Yes.
It takes light energy comes in, electrical energy comes out. Yeah.
But the energy that comes in creates power, right?
Power is just the expression of energy.
So if I said power source, it was technically right.
Sure. Okay. Other questions? I love this animation, and I totally forgot where I stole it from, but it's pretty cool. So, listen carefully, this is really important. All photons of electromagnetic radiation, by the way, electromagnetic radiation basically just means light. Electromagnetic radiation is radiation that comes from electrons or magnetic fields. So all electromagnetic radiation, light, has the same speed. In fact, if you like tables, this is the electromagnetic spectrum. I got this chart, the Advanced Light Source Lab in Berkeley, California. It used to be a particle collider back in the 60s, and they converted it to a light source lab. So there's electromagnetic radiation. So you got radio waves right up here. Radio waves are big, long waves the size of your house, or a football field, or a city, and they go right through you. Then you have microwaves right here. This is where you find your cell phones, right between microwaves and radio waves. Then you got visible light right here. This is infrared. Infrared's right here. All species exert infrared light. That's how night vision goggles work. Yeah, do you know you're emitting infrared light right now?
No.
Yeah, if you could see infrared light, you'd all look like angelic. If you could see infrared light, you'd all be like angels giving off infrared light. Yeah, so it turns out all atoms give off infrared light. And then you got visible light. This tiny slice right here, that's visible light. It is itty bitty. And then here's the UV visible light spectrum. This is also right here. This little slice right here, they stretched it out. So it's this tiny little slice right there, itty bitty slice. And then after visible light, you get UV. So that's ultraviolet right there. Ultraviolet light are smaller waves, but they're still moving the same speed. And then X-rays, gamma rays, and cosmic rays up here. Gamma rays and cosmic rays. Gamma rays are, remember gamma radiation? Gamma radiation is actually electromagnetic radiation. And cosmic rays are these super high energy waves